We are going live in 1, 2, 3, a few more seconds. We are live now.
Okay, do we have to wait until 8 o'clock or we can start now?
No.
바로 하면 좋다. Okay, now I think it's time. Good day, everyone. My name's Xia from Chinese National Group of Yangtze. Today, we're going to have a seminar talking about a very huge project in China. I would like to welcome everyone coming to our seminar. And before that, please allow me to take about 3-4 minutes to introduce the Yangtze as a tradition. So this event is held by International Association for Bridge and Structural Engineering. We call it YAPSI. And this is a very complex and very comprehensive association. And the goal of this association is to exchange knowledge and advance the practice of structural engineering worldwide. And for now, we have more than 100 countries. That means more than 100 national group in our association. Well, there are a lot of events held by the YAPSI Association. For example, every year we have annual meetings. It takes 2 days, and it's associated with the Congress every year. Usually it's in September. And upcoming event is the Yangtze Congress Inching 2026. It's held in Inching, Korea. And the next event will be in Guwahati, India in 2027, and also in the same year in Milan, Italy, also in the September. Well, we have a lot of publications associated with YAPC. For example, the first is Structure Engineering International. This is a journal, and it's SCI indexed. Second one is YAPC Bulletins. So we have a lot of YAPC documents, case studies, guidelines published with the bulletins. And also every year, when we have conferences, the proceedings will be published as well. And since we have so many national groups, and we also have independent activities from those national groups. And those are some sightseeing and also some online meetings, offline meetings in the national groups. Academically, we have technical commissions from 1 to 6, and also the task groups as well in each commission. And we care about young engineers. So there's young engineer activities as well. Well, today's webinar is actually part of the YAPC e-learning modulars. So besides webinars, we also have like keynotes from the conferences, lecture and online courses, reports, and toolbox. Those are available in YAPC e-learning. And now I think it's all free. Say tonight, the webinar will also be online, so for people to review. Also, there is a outstanding structure awards. For example, today this year, or say every year, we have a lot of outstanding structures applying for the YAPC awards. Also including the project today we're going to give a presentation of the we call it Nanjing Xianxin Road bridge project. So let's come to the seminar. Well, today's seminar is called the Nanjing Xianxin Road Yangtze River Crossing project. So the presenter is He Qiangtan, Mr. He Qiangtan. He's the chief engineer of this project, and he's from the principal design company called China Railway Major Bridge Mechanism and Design Institute. And the owner of the project is Nanjing Public Project Construction Center. So please, Mr. Tan, please share your screen and we can start the seminar. Thank you.
Yes, good afternoon, every sports. My sport title is Challenges and Innovation in the Nanjing Xianxin Road, Yangtze River Crossing, China.
Please full
Introduction.
screen. Okay, all right.
Introduction. Nanjing Xianxin Road, Yangtze River Crossing, located in China-Belize inland river port area, has a total length of 13.17 kilometers and is designed as a dual direction single lane urban expression way with a design speed of 18 km/h. The project consists of the main bridge, approaching bridges, tunnels, interchanges, and road bed. The main bridge is a single span suspension bridge with a main span of 1,760 meters. The approaching bridge is 9,985 meters long. The Wulongsan and Qixia tunnels has a combined length of 862 meters. Two full interchanges are constructed on the north and south banks, covered an area of approximately 90,000 square meters. Construction challenges: 1. Structural system challenge. The structural system of super long span suspension bridge is confronted with the problem of complicated mechanical behavior and poor durability. 2. City landmark challenge. As a key urban landmark in the city center, the bridge demands high-quality architectural and landscape design. 3. Wind and fire resistance challenge. It has low flat wind speed, significant vortex-induced vibration, and higher fire risks from hazardous chemicals. 4. Construction schedule challenge. The project is located in the urban central area, where on-site construction has a significant impact on traffic. Therefore, the construction period should be shortened. 5. Cost control challenge. There is a need to optimize the design of anchor foundation and the main cable material for better investment efficiency. 6. Equal sustainability challenge. Strict demands for eco-friendly construction, heritage protection, and full life carbon emission control must be set. Structural excellence. 1. Main bridge structure system. The main bridge adopts a 1,760 meters single span suspension bridge scheme to cross the Yangtze River. This design avoids impact on navigation and flood discharge, while taking into account waves, chemical ruins, railways, and riverside ecology. To reduce costs, the main cable is only cantilever over the main span. The side span of main cable is 580 meters, with a side to main span ratio of 0.33 and a circle to span ratio of 1/9. The sleeping girder has a width of 31.5 meters. The main cable transverse center distance is 27.7 meters. Given a width to span ratio of 1/64, the girder depth is 4 meters, with a depth to span ratio of 1/440. 2. Main bridge durability restraint system. The sleeping girder adopts a combined longitudinal durability restraint system, integrating broad rixus dampers, limited device, and central buckles. The force velocity relationship of the rixus flood damper follows the function F equal to CV alpha, where the velocity exponent alpha generally ranges from 0.1 to 0.3. Given an extremely low velocity, a smaller alpha value generates a large damping force. It generates almost no additional reaction to thermal deformation and provides immediate damping force for earthquakes and wind vibrations. With the assistance of this system, the daily cumulative displacement at greater ends is reduced from 80 meters to 9 meters, improving the durability of bearings, dampers, X-person devices, and short handlers. 3. Design of Stephen girder structure. The Stephen girder is made of a monolithic steel box girder. The top and bottom plates adopt U-shaped Stephen rivets. The top plate is 18 millimeter thick, and its U-rivet is 8 millimeter thick. The bottom plate is 10 millimeter thick, and its U-rivet is 6 millimeter thick. The longitudinal welds between the top plate and the U-rivet use double slide submerged arc-full penetronic welds. This can enhance the vertical performance of the orthogonal anisotropic plates and reduce the risk of brain deck cracking. The standard section of the steel box girder is 18 meters long, and a transverse gusset plate is set every 3 meters. For design of cable system, the main cables adopts the PPWS structure. Each main cable is composite of 169 strands, and each strand is made up of 127 high-strength steel wires with a diameter of 5.4 millimeters and a strength of 2,100 megapascal. The main cable has a diameter of 879 millimeters. The hangers are of parallel steel wire structure. The cable clamps are of cast structure, and a flexible central buckle is settled at the middle span to enhance the durability and service life of the short hangers. The main central is a structure combining casting and welding with a single longitudinal lever, while the space central is a cast structure with a support at the bottom. 5. Approaching bridge complete structure. To cross the Yangtze River levee, chemical pipeline, and railway, the first span arrangement of the north approaching bridge adopts an unconventional span layout of 50 and 60 and 80 and 100 and 70 meters. The main girder employs a corrugated steel web complete structure to resolve the difficulties in structural mechanical behavior. The main girder of the approaching bridge adopts precast steel concrete complete structure to reduce the self-weight of the structure. Partial piles and bent carpets adopt precast assembly, enabling standardized fabrication and accelerating construction, shortening the schedule, and minimizing traffic impact. 6. Tunnel structure system. The Wulongsan Tunnel is 247 meters long. To protect the cultural relics of the Wulongsan battery site, a tunnel on the pass scheme is adopted. The design method of constructing cut and cover tunnel by underground means is used. Solving the stress challenge of a large span minus the double arc structure on the class 5 weak surround rock. The Qixia tunnel is 650 meters long. A shallow buried tunnel constructed using the simple and direct cut and cover method. This results in a 5-leg transportation system. Elegant design of solution. 1. The story of N. The N-shaped pipeline design stood out from nearly 100 of proposals, highly recognized by experts and deeply loved by local people. Its unique cultural heritage tells the story behind it. The letter N shares a profound connection with Nanjing. Firstly, in history, the Yangtze River Channel originally featured an N-shaped platform. Secondly, Ning, a short form of Nanjing in Chinese, symbolizes the wish for the Yangtze River quality and peace. 2. The elegant design of bridge piling, inspired by the morphological evolution of the Yangtze River course. The N-shaped intercolumn joint stands as an emblem of Nanjing's past and present. Featuring a pair of anti-symmetric overlapping N-shaped motifs on both sides. The piling creates striking light and shadow effects by day, and showcases a four-season themed lighting display by night. As the four-season light and shadow rotate, the bridge is endowed with a dynamic show and the radiance of an ever brighter city. The 263.8 meter tall N-shaped main piling and the 1,760 meter main span Stephen girder, achieving a perfect harmony of rigidity and flexibility. Seamlessly interweaving the millennium old cultural heritage of the ancient capital with the majestic power of modern bridge engineering. The structural design of bridge pylons. The bridge pylons are of a mute-shaped frame concrete structure with two cross beams. The upper cross beam is a pre-stressed concrete beam covered with an N-shaped steel structure. The inner concrete beam and the tower column together form an overall load-bearing structure, while the N-shaped steel structure on the outside achieved the architectural landscape effect. Overall, it achieved a harmonious unity of structure, load-bearing, and agriculture landscape. The bridge pylons are supported by pile foundations according to the design of the friction piles. 66 broad cast-in place piles with a diameter of 2.8 meters are arranged at each bridge pylon. Creative innovation. Structural wind resistance. Ultra-long span suspension bridges face significant flat instability and wind resistant challenges, with long-term degradation potentially triggering vortex-induced vibration. Focusing on optimal wind resistant design at a 0 degree angle of attack. The project team optimized the steel box girder cross section and at over 30 wind resistance via wind tunnel tests. Finally adopting 1 meter wide horizontal guide plates on both sides, plus a 0.67 meter high upper central stabilizer plate. This configuration increased the critical flutter wind speed to 70.7 meters per second, exceeding the fabrication wind speed of 60.3 meters per second. Vortex induced vibrations were fully suppressed at a low damping ratio of 0.1%, and this design provides a damping reserve safety margin and greatly improves the structure wind resilience. These are wind tunnel test models of different central plate. The left is no central plate. The middle is 0.667 meter central plate. The right is 1.02 central plate. Fire resistance and disaster resilience system. The bridge connects riverside chemical industrial parks, pulling high fire risks from hazardous mechanical vehicles, and challenging its fire resistance and disaster resilience. For the first time, a quantitative model for tanker fire was established in the project. High temperature stress strain curves, as well as reduction factors for strength and electrical modulus, were obtained through tests on 2,100 megapascal steel wire. The fire resistance limit of the cable system was determined via numerical analysis, taking structural safety and fire protection continuous into comprehensive consideration. The fire protection objectives were defined as when cable surface temperature below 300 degrees centigrade and steel component temperature below 550 degrees centigrade after 45 minutes of combustion. A complete fire resistant tank consisting of main cable, aluminum foil, and high silk fiber was developed, and an integrated protection system of epoxy fire retardant coating plus anti-corrosion coating for steel components were proposed. With a protection height of 60 meters, it can withstand fire up to 1,200 degrees centigrade for 45 minutes. A systematic summary of fire resistance technologies was conducted. A 3-level fire resistance objective for cable systems was established, and the guidelines for fire resistance design of highway bridge cable systems were complied, filling the gap in fire resistance design standards for cable-supported bridges. Anchor foundation design method. Ultra-long suspension bridges anchor foundation are extremely large scale. To improve cost efficiency, the team developed an isotropic constitutive model accounting for soft soil creep and small strain stiffness effects, validated via triaxial and splitting tests. The model clarified the soil plastic and deformation load and foundation ground coordinated bearing mechanism, enabling the first level anti-slip and anti-overturning design method for under foundation, considering soil resistance. This method optimized the south anchor diaphragm wall and the north anchor open case, cutting overall foundation value by 12% to 15%. Anchor design. The main cable anchorage system is made of steel structure and is coated with isolation and anti-corrosion laid around it. Secure south anchor diaphragm wall, diameter 65 meters, height 62 meters. Rectangular north anchor open case, length 70 meters, width 50 meters, height 50 meters. Research and application of new 2,100 megapascal steel wire material. Ultra high strength steel wire pulls the main cable load bearing capacity and span potential to improve its toughness. Technologies including ultra purification, including harmless smelting, and online water quantity were adopted. Refine the microstructure to over 90% solvite content, 100 to 150 nanometer diameter spacing, and grain size above grade 6. Optimize the lubrication during wire during suppressed residual stress and service cracks, enabling the development of 2,100 megapascal main cable steel wire that meets all technical requirements. The test was conducted for more than 20 times of torsion, 8 times of winding, 4 times of repeated bending, and 2 million times of fatigue. Each application cut steel consumption by 7,143 tons and saved 110.7 million yuan Chinese. Sustainability, carbon emission assessment. To implement the dual carbon strategy, the scheme proposed a carbon emission verification method for large suspension bridges. It established the carbon emission evolution indicator and system, and developed a carbon emission indicator database and accounting system. By decomposing the carbon footprint into each process using WBS beam component units through secondary development to match the coding of the beam model with the unit process, and combine the carbon emission factors in database, and energy consumption and carbon emission were calculated. This successfully reduced 36,000 tons of carbon emission, protected the environment, and formulated the formulation of technical guidelines for carbon emission accounting in highway suspension bridge construction. Main cable dehumidification system, ETFE membranes including is firstly applied to the anchor chambered steel structure, cutting the dehumidification space by 65% to realize target dehumidification and easy to maintain intelligent system. Based on the calculation of the HVAC in self-humidity diaphragm, automatically correct the operating indicator and developed an intelligent control type variable dehumidification system with balanced dehumidification effect and energy consumption. Double soil mixing column method. The soft anchorage diaphragm wall foundation lies on deep below plastic soft soil. Required 51.7 meters trench wall reinforcement. The reinforcement of the slaughter wall of large suspension bridges mainly adopts the deep mixing pile or high pressure jet grounding pile technology to penetrate the soft soil layer. The reinforcement depth is generally no more than 20 meters. However, when the reinforcement depth exceeds 30 meters, using the above mentioned conjunction method is difficult to control the wall forming accuracy and the CPG prevention effect of the continuous wall. The team pioneered the double soil mixing column method to tackle CPG and deformation issue in deep large pits, while achieving 100% slurry recycling to protect the adjacent ecology park. Zero discharge, zero pollution. Precision monitoring and control system. Traditionally, the local measurement system is generally used to measure the mud surface elevation during the sinking process of the open casing. However, this method is slow and has poor accuracy. During the sinking process, accidents such as tilting, sudden sinking, and cracking are prone to occur, which makes the handling very troublesome. Based on ultrasonic echo and failure principle, this project developed the world's first precision monitoring and control system for open casing mud surfaces. This method is highly accurate and can also be used for timely measurement and control. Replacing traditional measuring ropes, it achieved zero ground disturbance during precise sinking of the North Anchorage open casing, ensuring the safety of adjacent railway and the Yangtze River embankments. Conclusion: Nanjing Xianxin Road Yangtze River crossing has achieved remarkable results in instruction excellence, elegant solution, creative innovation, and sustainability. It has formulated 3 standards and specifications, saved 350 million Chinese yuan in investment and promoted technology progress. It has become a new landmark and a popular spot for photo taking. The technology developed in this project has been replicated in multiple projects in other fields, such as highways, railways, and municipal works. That's all. Thank you for your attention.
All right, thank you very much, Mr. Tan, for the presentation. Well, generally speaking, Well, this bridge is, or see, this crossing project is fantastic. The suspension bridge spanned 1,760 meters, and now it's the third longest suspension bridge in the world. So we can see there must be a lot of challenges, a lot of problems when we design and construct and maintain this bridge. Also, I think it's time for the audience to raise questions. We have already shared the presentation in PDF format in the, I think we shared a link. So for those who are interested, you can download the PDF from the Q&A session. So there's a link there, and this is shared by the presenter and also the bridge owner. So there are a few questions, so I'll transfer those questions to the presenter for them to answer. I think the first question is, what other shapes or devices were considered for vortex-induced vibration? I think the audience is concerning about the wind load, because this bridge is so large. So they want to ask if there's any special device were used for the vortex-induced vibration. 风致振动有什么措施？
Okay, I'm the assistant of Miss Kang. Let me share this question, and I will go to the back page. Here we have two kinds of plates here. Number one is the number one. We have the horizontal guide plates here. There are two plates on each side of the girder, with the width of 1 meter. 1 meter, okay. And there is a single upper center stabilizer plate with a height of 0.67 meter here. And we can see the curve, which many measures test about 30 measures test according to the presentation just now. And here we have a graph here. If we don't have any center plate, the lateral critical wind speed is about 60 meters per second. If we have 0.67 meter center plate or 1.02 center plate, the speed will increase a lot to about nearly 90, about 85 meters per second. So this is one kind of the up center plate here, but finally we choose the 0.67 meter center as the ultimate design.
Okay.
Okay.
Yeah, okay, all right. Thank you. I think it's very clearly answered. And also followed by the previous question, there's one more question also asking about the same similar concerns about wind resistant performance. And this is also answered as well. Yes, usually for this kind of long span bridges, they always do like CFD numerical simulations and also the full scale wind tunnel test. And this is like for every long bridges in China. Okay, let's come to the next question. Gaurav asks, the motivation behind the N shape is quite inspiring to have been chosen by people and having represented the identity of the city. So my question is, why was the hybrid approach of using inner concrete and outer N-shaped steel structure chosen for the upper crossbeams of the pylons? So they want to ask why this kind of shape. Maybe I can answer first. They ask why is N? I think N shape is like the initial of the Nanjing city, so it's N.
Yes.
And why inner concrete and outer N-shaped steel structure? So maybe you can answer that, add up more information.
Yes, as is known to all, we choose the N-shaped pylon as the signal as our bridge, and we know that is the history of Nanjing. But the N shape is a 3D surface solid. Yeah, and it is not. It is a very complicated shape. It is not very suitable for the horizontal force to suffer these two large force here. So we use a concrete beam, and this concrete beam is strengthened by the pre-stressed here to make the two columns more rigidity. Yes.
Okay, there is one more question regarding the N-shaped pylon. George asked, was it not possible to incorporate the N-shaped link into the load carrying system, given that the optimization of materials was a major goal of this project? Well, I think, are you going to answer it,
Yes,
or you want me to?
we did think this method, this idea, but we tried this for several models. But it is not suitable for the steel component. It is not suitable for steel component to fix to a concrete column properly, because the when we use some connection, for example, weld or voided connection, it is will make intensive stress. Yeah, that's the answer.
All right, thank you. Let's go to next question. How do the two anti-symmetric N-shaped patterns on the pylon change? Do we have a spatial model illustration? This question is also about the pylon.
Yeah, we have a model. I can show all of you. This is the 3D model of our pylon, and we create a 3D surface solid body here just to illustrate the two N signals from one side to another. How do the two ends change gradually from one side to another? If you look from north or from the south, you will notice this is the still same end here, not anti-Semitic end here. So that is another reason we choose still structure as the end shape.
All right,
Okay.
thank you. I think there are a lot of questions about the wind resistant and also seismic analysis. So and also the end shape carries a lot of attention. So the next question is, from a seismic point of view, is a bridge located in an area of low, high, or moderate seismic activity? So longitudinally, what retaining system was used? So this is about seismic.
Nanjing is in the earthquake zone of the Grade 7. That is not very serious degree here, because the most degree is 9. In China code, there are 4 degrees. From 6 to 9, there are 4 degrees, 4 grade here. We
Okay,
have some
instead, go ahead.
about the earthquake retaining system. We have 3 devices here. Let me show you. There are 3 methods here. Number 1 is the viscous fluid damper. This is the picture of this device. Number 2 is the limiting devices between the tower and the steel girder. And the third one is the center buckles, just in the middle of the main bridge span. All 3 together make the main bridge with the long span of 1,760 meters. The large bridge move smoothly and safely during the earthquake. Okay, that's all.
All right, thank you. Besides wind and earthquake, I think the one point of this research is to consider the fire. So this is one of the innovation of this project.
Yes, we did much research work about the fire resistance and the disaster. Here we do many research work. Here, this picture shows us the tidal flame. That is the flame of the fire. Fire source is here, and we can see the radiation receiving and target here. Another one. Another one is the strain and stress curve of of the steel. You can see here, during different temperature, the stress and strain curve are different. From 100 degrees centigrade to 700. And this one is the yield stress. Yield stress, according to the time passed by, the main cable stress is almost like this, and the yield stress decrease sharply. Also, do some calculating, simulating work on the computer. For example, this is the temperature counter. We should make the temperature field, temperature condition, input the temperature condition into the model, into the solid model of the ANSYS, and we can calculate the deformation counter here, and we can also calculate the plastic strain, plastic stress, and the deformation about the stiffener plate. According to the simulation work, we design some coating here. For example, for the main cable, we give this coating system. This is reflective, fire resistant material. And the second is refractory binder. This is the middle layer. And the third is thermal insulation and fire resistant material. And we can test, we do many tests here. This is the burnt bridge after burning. Okay, you can see it is seriously destroyed by fire. And this is the coating for the joint of the cable. This is the coating for the suspenders and the main cable. After all the protection system, our steel components have very good behavior under temperature and the fire and the high temperature or fire disaster. We can see the dash line with different colors are much lower than the allowance 550 degrees centigrade. Okay, so.
All right. Thank you very much, Ms. Chen. I think we have already answered mainly all the questions raised by the audience. I think the project, I personally is very proud of such kind of huge infrastructure. I think I would also like to thank the presenter, Mr. Tan and Ms. Chen, for answering those questions and giving us this kind of presentation. And also thank you for sharing the slides with the audience. So for audience who are interested, you can find in the chat room, there is a link so you can download the slides. If you have any further questions, you can email the YAPSI secretary. So they will transfer those questions to the presenters. Okay, I think I will close the session today. thank you all for attending this event. Thank you very much. See you later.
Okay, thank
Bye.
you, Professor. Yes, thank you, everyone. It's our honor to show